We start this, I can say, really great session, because this event quantum community expected for many, many years, and during this conference there were a lot of critical discussions where people do not believe that such experiment will be done at all, but experimenters are more clever than theoreticians, and sometimes they do what theoreticians think is impossible. And today we have really great possibility to see all three these experiments which were done last year. Today my proposal is that we should not discuss so much interpretational issues, because today is the day of experimenters. They did excellently their job, and maybe next 20, 30 years we shall discuss possible interpretation of the results, but today we should... Too short, okay. So today we should just see these experiments and discuss statistics, discuss these experiments, and maybe make some conclusions or critical analysis. So the first speaker of this session should be Professor Alain Aspect, but unfortunately due to this double strike of two air companies he was not able to arrive. And Philippe Grangier, who knows very well views of Alain, and it would be joint presentation of your views, as I understand. Yeah?
Thank you very much. Thank you, Andre. So, well, I am not Alain Aspect, so I could not make it due to the Air France strike. I was very sorry for that. So he told me he was actually planning to speak to you about experiments they are doing now for Bell tests with matter waves. They do experiment with helium BECs, they extract matter waves, and like that, you may hope it's not working yet, but this might yield a new Bell experiment. But so I'm not involved in this experiment, so I will speak rather, I agreed with Alain about that, about experiment we did together, but about 35 years ago in Institut d'Optique, which was all centered on the Bell's inequality test, which is the main topic today. So I agree with Andre also that I will use this opportunity to give some kind of an historical introduction to the subject. So this was our building 35 years ago, Institut d'Optique in Orsay. So you are welcome to come, but actually we are not here anymore. We moved to a few kilometers away. Now we are, Institut d'Optique is now called Institut d'Optique Graduate School. It is in Palaiseau. We have a brand new building. If you come, Alain is still there. I am still there. Our co-workers, Jean Dalibard is now in Collège de France, and Gérard Roger, who was an optical engineer, is happily retired in the south of France. So we have in this new building we have a little museum actually, and several pieces of experiments that I will show today are in this museum, so you can really see them if you come. Okay, so to start, I think it's very fair to start with Einstein, who, as you know, has had a very major role in quantum physics. He is clearly one of the main founding fathers of quantum physics, but also the author of very strong criticism about what it means. So one of the main contributions of Einstein to quantum physics, he had many contributions to physics, but let's speak about quantum physics, is a very famous paper on the photoelectric effect in 1905. So it's by analyzing the photoelectric effect, you know that, he deduced that light is made of least quantum, which became light quanta, and then photons, which have a well-defined energy and momentum. So this Einstein paper was a very big shock at that time because it was contradicting Maxwell equations, which were extremely well established. So it was sort of completely absurd to put grains of energy in a wave model. And this was actually rather strongly rejected. So there were many experiments. So when you have a crazy theory, you do experiment. So Millikan did experiment during 10 years from 1905 to 1915. He wanted to prove that Einstein was wrong, and he proved that Einstein was right. And so it was a triumph for the photoelectric effect. As you know, Einstein got the Nobel Prize not for relativity, but for the photoelectric effect in 1921, and Millikan for the experiments about the photoelectric effect in 1923. 1922 was Niels Bohr, yes. Okay, so this is a photoelectric effect. So now what Einstein did also, which is very famous, is this 1935 paper where he looked at what we call now entangled states. So it's basically two particle sets with quantum correlation between them, and this yields very strange effects. So this was spelled out in this very famous paper, EPR paper in 1935. Can we consider the quantum mechanical description to be complete? So the idea of this paper, I will not give more details here, but it's basically they proposed a simple definition of reality and locality, which was based on Einstein intuition, and which is very, it's a way to represent what we think, especially in classical physics and relativity, about what is reality and what is locality. And from this argument, this definition, they deduce that the quantum formalism is incomplete in the sense that there are some physical quantities that you would expect to get values, but they don't get values. In the quantum formalism, you are not allowed to give values to these quantities. They are undetermined, let's say. Again, I will speak a little bit more this afternoon about that, but here it will be enough. So the conclusion is that it was a little bit like quantum mechanics was hiding some information from us. So this paper was published, and there was an immediate reaction by Niels Bohr, which published a few months later another paper with exactly the same title, telling just the opposite, that quantum mechanics is complete. So this triggered a very intense debate over many years. You know, Einstein and Bohr here arguing and arguing. The impact of this discussion was not extremely strong. And the main reason for that is that quantum mechanics was working just incredibly well. So it accumulated success about understanding nature. You know, atoms are not stable in classical mechanics. Electrons should radiate and fall on the nucleus. So simply the stability of matter is a quantum phenomenon. So you have the structure properties of matter, conductors, semiconductors, superconductors, quantum theory of light, photons, interaction between matters and light. All this works incredibly well. We know that. Also, there were new concepts, invention, transistor, lasers. So this is just a long list of success. Also, a point in this debate is that basically there was no disagreement on quantum predictions, on what you can measure. So if there is no disagreement, quantitative disagreement, then the debate can be considered as philosophical, and then, okay, well, it was sort of put aside. But then it completely changed in 1964 with the story of Bell's theorem. So John Bell proposed a way to sort of materialize this debate and turn it into an experimental thing. And this completely changes the landscape and had a very deep implication. So I don't know whether you saw John Bell, so I will show you a short document which was a conference. It's the beginning of a conference by John Bell in Trieste in '89. The conference was organized by Professor Girardi, so he sent me the CD. So this is John Bell here. He will be introduced by Alain Aspect. So you will see Alain Aspect speaking with his famous accent, which cannot be missed. So Alain will introduce Bell, and you will see just the beginning, the 2 first minutes of the talk by John Bell. If you want to understand, he will tell a little story about Paul Dirac and Werner Heisenberg. To understand the theory, you should remember that in quantum mechanics, you cannot know before the measurement is done. Okay, so let's go.
It's a great pleasure and an honor to introduce Professor Bell. Many of us have been strongly influenced by his work of John Bell because obviously he has shown us that quantum mechanics is much more difficult to understand than we thought it was. And I'm sure that today he will again raise some questions which are very embarrassing, but that we have definitely to face. This is a picture of Dirac and Heisenberg. Many direct stories were told, and some of them are very relevant for what I have to tell you. I'll start with one told by Heisenberg.
So it's a story told by
Heisenberg says that Paul always thinks about his formulation very carefully. He does not like to answer spontaneously at once. He first thinks about things
as you can see, so John Bell was sort of, he liked to tell such stories, but okay, so the serious stuff is Bell theorem. So I'll make a very short account of Bell theorem. So the idea of Bell theorem was to sort of exploit these ideas of missing variables or hidden variables introduced in the EPR paper and to deduce some quantitative consequence of it. So you have to consider entangled particles. So these are basically, in the experiment, it will be 2 photons emitted by a source in an entangled state. On these photons, you can measure polarization, which means that you put a polarization on the way of the photon, and then the photon can be, there are 2 outputs that are labeled like +1 and -1. It's very similar to a Stern-Gerlach experiment for a speed 1/2. So there is an orientation for this polarizer, and then you can rotate this A and get some result, and on the other side, rotate the B for the other photon and get also +or -1. So Bell's idea was to so if you do that, the results may be correlated. Correlated means if you get 1 on one side, you will also get 1 on the other side. So Bell introduced what is called supplementary parameter or local hidden variables in the spirit of Einstein on EPR correlations. So you assume that this lambda will simply determine the result +or -1. This is a very simple demonstration. There are more sophisticated demonstrations, but this one is enough. So the result depends on lambda, the property of the photon, and obviously on the orientation of this polarizer on this side and not the other one. Same thing on the other side with the other polarizer, and the lambda is a shared property from the source, and these lambda are random, and they have a normalized statistical distribution. Then, if you have correlation, you can look at correlation. So these are 2 random variables. So typically, correlation function is the average product. So if the average product is 1, it means you always get +1, ++ or -. If it is -1, you always get +- or -+. And if it is 0, you get anything. So the average product of this A and B, which is called the correlation function, is a way to measure correlations. So what Bell did is that he looked at this correlation function, the average product of A and B, and then it's a 2-line calculation. I don't show it, but it's in hundreds of books with 2-line calculation from this hypothesis. You deduce that this quantity S, which is a combination of 4 correlation functions, has to be bounded between -2 and +2. And these are the famous Bell inequalities. So you see, what is absolutely fantastic in these inequalities is that they come out of the blue. It seems you assume almost nothing here, but this nothing is not nothing at all. It's a very powerful hypothesis, and then you get this bound. But then, if you look at quantum mechanics, then the value of S can reach 2 square root of 2 for a given choice of angle, and then you end up in a conflict. Which is Bell's inequalities, Bell's theorem. These simple hypotheses are in contradiction with the prediction of quantum mechanics. So this was in 1964. It took some time to realize, but then after that, obviously, experimentalists were interested in this question, and they wanted to measure it, because you can measure here, you can do that, you can calculate this E, you can calculate the S, and then get the value and see what happens. So there were many. The first experiment started in the 70s. John Clauser did the first one. First, there was a little bit of reshaping of the inequalities. So the most famous one called CHSH by these people in 1969. Then John Clauser, in an experiment in 1952. It was very, very complicated experiment. No laser at this time, hundreds of hours of counting. But finally, get a good agreement with quantum mechanics and the violation of Bell's inequalities. The experiment was done with slightly different parameters by Holt and Pipkin, and they found Bell's inequalities. Quantum mechanics was wrong. So the 2 first experiments were contradictory. So Clauser redid Pipkin experiment and found again quantum mechanics, and then Ed Fry, now with lasers, did it again, and so it was clearly going towards quantum mechanics. So then the second generation was initiated by Alain Aspect in Institut d'Optique. So we had now very good laser, I will show you, so we could get a very good source. So we could sort of remove imperfection of the experiment, and the main idea introduced by Alain was to test quantum non-locality. So I will explain that later. So this was the main difference between the whole previous generation. So this was done in 1982. Then, in the next years, there were many, many other experiments trying to sort of improve this locality condition, get more efficiency in the detection. I will also speak about that, and you will hear a lot today. Gregor Weiss will give an example of this family of experiments. And finally, the big event today is that last year there were 3 experiments which eliminate sort of all loopholes. So they are really a materialization of the ideal experiment and still get an agreement with quantum mechanics. But you will hear more later about that. So this was our experiment in 82. So we use the same cascade as John Clauser. So it's a calcium atom, so in an atomic beam. So the calcium atoms are excited by 2 lasers, and then they emit 2 photons. And you have angular momentum conservation, which tells you that these 2 emitted photons, the green one and the blue one, are in this entangled state, which is the one you want. So the calcium atoms were in an atomic beam, so this was a vacuum chamber here. So it was excited by a Creighton ion laser. This is my first laser I worked on when I started as a student to lock it on there. Okay, so you see it from the other side. The Creighton laser is here. It goes to the calcium atom, and on the other side there is a tunable dye laser, rhodamine 6G, which also excites the atoms. So the excitation of a 2-photon transition is usually weak, but with lasers we could get very high excitation rates, and so many pairs. So we had typically 100 counts of pairs per second. So you get 10,000. 1 over square root of n is 1% with 100 seconds. So what can you see here? So these are the lasers. These are the big, ion lasers, which are completely obsolete now. Rhodamine 6G is sort of obsolete now also. But this was how it was working. So we need also polarizer. So a trick was you need very good polarizer because you work very hard to have these photons. You don't want to lose your photons. So you want that the good polarization is transmitted with a very high efficiency. But the bad polarization should be the other one, should be removed. So a way to do that at the end of the 70s was to use pi of plates polarizer. So probably Brewster angle. So if you have a plate, the light comes from here. So this is a plate. And if you go to the Brewster angle here, this polarization in the plane of the screen is transmitted with unity, and the other polarization is partly reflected. So the good polarization is always transmitted, and for each plate you remove a little bit of the bad polarization. So with 10 plates, you remove it more or less completely. So you get a good polarizer which have a very high transmission for the good polarization and a good extension. So they transmit like 98% and the extension is like 1%. So this was already used by Clauser. So they are pretty big devices. You can see them in the museum now. But it works pretty well. So you have to rotate this thing in order to make polarization measurement, and behind you have photomultipliers. So, well, we did an experiment. It worked. We also sort of removed we pushed away the polarizers in order to check that even if the photons fly apart a significant distance, it's still violating Bell's inequalities. So you see you have pipes here. So this is, for the green photons there was a green pipe, and for the blue photons there was a blue pipe, so that they can find their way. This was a local joke. The pipes were just for stray light. They were not evacuated. It was just to protect from stray light. We did this experiment. So this first experiment here, so we obtained a violation of Bell's inequalities with a significant amount, even by increasing the distance, but everything was static. So the next step was to use what we call two-channel polarizers. So in the previous type of polarizer, the good photons were transmitted, but the bad one was lost. So it's not very nice. You would prefer to have really plus and minus outcomes. So with two-channel polarizers, you can get that. You have two channels, two photomultipliers. Now you get two clicks corresponding to plus and minus 1, and the correlation function is very easy to calculate. So you just make this ratio. So due to the epsilon, plus makes plus, minus makes minus, but here you have plus minus makes minus, and minus plus makes minus, and you divide by the sum, and this gives the correlation coefficient. So you directly get what you want to measure for a given value of A and B, and then you switch the A and B, and the experiment is done. So there is a so-called fair sampling approximation, because actually we miss a lot of pairs. So only the counted pair are counted by definition, and you have to assume that this the detected sample is a fair sample of all the emitted pairs. So this is a very strong assumption, but you will see better in the next talks. So this was done this way. So this was a setup. So this is a rotating stuff. You have the two photomultiplier, which are big tubes, and the cube was inside. So actually it was funny with this cube. So this was Alain at that time. So one weekend he went to Amsterdam with a big suitcase. So when you go to Amsterdam from France with a big suitcase at the end of the 70s, it may be a little bit suspect. So he came back from Amsterdam with a big suitcase and a big smile. So I really wondered what was in this suitcase. But what was in the suitcase were the polarizer cubes, which were done by Philips. He had a friend in Eindhoven, and so he sort of smuggled in the polarizers from Amsterdam. And so these are... Okay, if you know Alain, you appreciate his smile. You can imagine easily his smile when he came back. So this was a result of the measurement. So now with the full S parameters, these are the Bell limits. And so this is a theory according to quantum mechanics and to the real performance of the experiment. There is this maximum violation here. And you see the agreement with quantum mechanics is absolutely excellent. It fits within, so he's saying in order to see them, it's plus or minus 2 standard deviations. The value of S here measured is 2.7. And so if a violation of this one by about 40 standard deviations. So it was, at this time, it was, I think, the best static experiment ever done at this time, because both the violation is very strong, the agreement is excellent, the statistics is excellent, but it's a static experiment. Then Alain got another idea. So you recognize my haircut. So actually, he did not get this picture was taken around 85, I think, but he got the idea before. So the idea is a big idea that he published first theoretically in this paper in '76. This is about this Bell locality hypothesis. When you assume in the little calculation that A depends on big A depends on small a, you make a strong assumption, which is that it does not depend on B on the other side. Same thing here, and you also assume that rho, the distribution of the pairs, does not depend on A and B. So this is a locality hypothesis. So Alain's idea was to say that if you move actually the polarizer fast enough, we use variable polarizers with a switch faster than L over C, then in some sense relativity will enforce this condition. So from relativistic causality, if you believe in relativistic causality, then you cannot have a B here, because simply the information has not enough time to travel from one side to the other. So all the idea is to switch very quickly the polarizers faster than the travel time of light between the source and the polarizers. So you cannot move, it takes a few billions of seconds, so it's not possible to move a polarizer that fast. But Alain's idea was to use switches. So you use a switch here, which is a very fast switch, which sends the lights either to one polarizer in orientation B or another one in orientation B prime. Same thing on the other side. So they have to be very fast and sort of binary. You don't want to lose light again. So it should really switch between this and that very quickly. So it took some time to set up, but these are this famous switch. So this is a switch. So they are basically water tanks. So it's about that size. It's filled with water, and there is a standing wave in the water. When the standing wave is off, the light goes straight. And when the standing wave is on, the light is diffracted and so deviated. So this was the switch. So this was a switch in place in the experiment. And so there was a switch to two different tubes here with two polarizers and photomultipliers. So the idea is, as I said, so you have a standing wave is water. These are lithium niobate transducers. So when the standing wave is 0, it goes straight. And if you have this oscillating standing wave at 25 megahertz, so it makes a 50 megahertz switching between the transmitted beam and the deflected beam. So the timing is just right. So there is no, not much margin, but you go from maximum here to maximum here every 10 seconds. And the travel time between polarizers is 40 nanoseconds, and between source and switch is 20 nanoseconds. So, well, just okay. So still, you can expect that by doing that, if there is an effect due to the switching, you should see it. You should see something. So we did this experiment again. So it took a lot of time because you have to accommodate the switch. So the counting rate was much smaller. So we had reduced signals, so longer counting time, data accumulation for several hours, not hundreds of hours like Lauser, but several hours. But you know, Alain is from southwest of France, so he brought to foie gras and sauterne, and we could usually, you could use the time in a nice way while photons were coming. The switching was not fully random, not extremely fast, and you will see much, much better in the following experiment. Still, again, this gives a violation of Bell's inequalities by 6 standard deviation, a very good agreement with quantum mechanics. Each measurement was spectrally separated from setting of the different polarizer, and so in some sense it was sort of Einstein's causality was enforced, not as much as one would like, but at this kind of numbers that I gave suggested that if there were an effect, we should have seen it. Here, everything remained correlated as predicted. Okay, so well, this is not completed. So what at this time, what did we say? So these are was already an early but not complete failure of local realism. So local realism is a short term for Bell's hypothesis. So Einstein spoke about that already. What would be the consequence of a failure of the imperial reasoning? So Einstein said, so either drop the need of the independence of this physical reality present in different parts of space, or accept that there is some instantaneous influence at a distance. So this is very weird because everybody knows and everybody agrees that there is no faster than light signaling in this experiment, but well, it's a famous quantum non-locality we are still thinking about. So this is also a mystery. On the positive side, it was quickly realized that entanglement is very useful, and it was also the start. You know, in '82, when we did the experiment, was the same time as Feynman proposed this idea of quantum simulators. Then there was quantum cryptography in '84, quantum teleportation in the '90s, quantum computation, information, etc. And so everybody knows now that entanglement is absolutely essential for all these quantum information applications. So it's mysterious, but it's useful. And you will certainly hear more about that in the next talk. Another funny thing is that Institut Optique is an engineering school. So now our students are trained in testing Bell's inequalities. So you see, you have gyrometers, Raman scattering, and Bell test in the little book. So a Bell experiment now looks more like that. You can forget about the dye lasers, the atomic beams, etc. It's just a small blue diode laser here and crystal. Then you have polarizers and avalanche photodiodes. So you will see. So it's about that big. Instead of this full room of equipment, it's something which is that big, typically the typical student gets S equal 2.3 within one afternoon. Okay, so well, I think I will just leave the last word to Bell. So this is extracted from a talk by Bell in 1980 in Orsay, just before the result of the experiment. So, well, you say, let us anticipate that quantum mechanics works also for ASPE. ASPE means the switches. It was just before. How do we stand? So I will list 4 of the attitudes that could be adopted. The inefficiency of the counter and so on are essential. Quantum mechanics will fail in sufficiently critical experiment. This was quite relevant for our experiment. You know, well, you will know before noon that it's no more the case. So you can forget about inefficiencies. This is not the problem. So then another one is there are influences going faster than light, even if we cannot control them for practical telegraphy. Einstein local causality fails, and we must live with this. Okay, well. Another option is the quantities A and B are now independently, so you can survive. So this is a so-called, I removed a little bit of it, it's a so-called superdeterminism. Everything is sort of written from the beginning of the universe, and your random choice are not random at all, and then you can do whatever you want. It was written anyway, but it also kills free will. So it's, well, okay. So it's also sort of a shaky option. Well, the last option he gave is the full analysis can be simply ignored. The lesson of quantum mechanics is not to look behind the prediction of the formalism. As for the correlation, well, that's quantum mechanics. Okay, so none of them is really satisfactory. But Bell was wise enough to say 4 of, and well, you have probably your own one. I don't know which one, or another one. And we will certainly hear more about that today. Okay, so thank you for your attention. I'll stop there.
Yeah, maybe we can ask a few questions about this historical introduction. Okay, Theo, yeah. No, okay, you just don't know. Okay, Nicholas. Yeah.
Well, I was still young, you know, and I was really sort of anxious to know. No, I was not expecting anything. And you know, there is this very famous...
Not expecting anything?
No, I expecting something, but I could not, you know, bet. Even my agent heads, cubist agent S, was not able to bet what would be the result. Also, you know, there was this very special style of Alain that he did not want to make experimental trials. He wants to get everything absolutely perfectly right, every little details, and when we are really, really sure that all counters are perfectly working, all logs are perfectly working, then we do the experiment once. And this is what happened. That is, we worked a lot, that, and everything was fine. One good day, we brought the foie gras and the champagne, and and then we counted. And the first time, the Bell's inequalities were violated. After that, we repeated and repeated to accumulate statistics. But there was no trial and errors. It was just done once. And so I think it was pretty impressive. Yes.
Since the question is about what everybody has expected before the experiment, I would like to refer to John Clauser, who, it has been mentioned, has done the first conclusive experiment, and he told to many people, including you and others, that he actually expected quantum mechanics not to work out. His position was basically, this is now my words, that nature can't be so crazy. And that speaks very much to the quality of an experimentalist, that he does the experiment in such a way, well, the result is different. We have to accept it.
The story is about the same about Millikan. Millikan, with the photoelectric effect, is very famous that Millikan wanted to demonstrate that it's wrong, but he sort of demonstrated himself to be wrong just by doing careful experiments.
It even goes beyond, because the experiments that actually failed to violate Bell inequality by Holt and Pipkin, they were actually in favor of quantum mechanics.
Yes.
So the two first experiments found exactly the opposite of what we were expecting.
Yes, it's strange.
You showed us a very nice lineup of 10 Brewster plates. And then you only showed us one beautiful, but still just one beam splitter.
Yes.
How did the purity of the transmitted beam and the beam splitter compare to the 10?
It's similar. It's a multi-dielectric coating, so instead of having 10 plates, you have interferometric coatings on the diagonal. And so the performance of these cubes were pretty good. The transmission was sort of, I think, about 95% for the good polarization, and the extension ratio was also in the percent range. So they were more or less similar in terms of transmission and but with the cube you get the other photon, which is a major advantage.